Hello there, welcome to the session of the friction. In this video lecture, we are trying to learn the laws of dry friction. This is connected to the last video lecture where we are trying to define what is the friction, what is the limiting friction, and how this resistance force is developing, and after certain time when the applied force is going to be more than, then automatically the friction is going to be why it is decreasing. Those we have discussed in the lecture 29. So now we are going to be defining what is the laws of the friction. So here the laws of dry friction. The law here is that, in simple words, we are going to be say the friction which is developed between the two contacts, it is independent of the area contacts, but only it is depends on the surface asperities. See, that's what he is saying. The total friction that can be developed is independent of magnitude of the area in contact. What is the second law? The total friction that can be developed is proportional to the normal surface is transmitted across the surface of the contact. In this case, the frictional force is directly proportional to the normal reaction force. So then what will happen in this case? Then how we are going to be developing the frictional force in terms of the mathematically? In this case, the frictional force is directly proportional to the normal reaction. The third one is that at low velocities or low speeds, the total amount of frictional force that can be developed is practically independent of velocity, but the force necessary to start the motion is greater than the necessary to maintain the motion. So in this case, what will happen? Whatever the frictional force is developing, that is considering at the low velocity, is independent of that part. That means the velocity at low velocity side, that is not influencing on the frictional force. So here I would try to take the second law and we will try to see how these forces are going to be directly proportional. The total frictions that can be developed is proportional to the normal force transmitted across the surface contact. That's I am going to be taking here. The frictional force is directly proportional to the normal reaction. That normal reactions are represented in N, and this is the F. I am going to be removing the frictional constant, that means proportional constant. I am applying the one more constant that we are going to call the coefficient of static friction. That is F is equal to mu into N. Here M is going to be the frictional force and N is going to be the normal reaction and mu is going to be the coefficient of friction. So coming to here, how to calculate the angle of friction and resultant reaction. As we know that in this case, the normal reaction and the limiting force acting at all the surface of the contact, they combine into a single resultant called the resultant reaction at the point of contact. These fundamentals we have seen in our concurrent forces. In the concurrent forces, when the number of forces are going to be acting, that's we converted it into a single resultant force. So that whatever the effect is going to be generated by the number of forces, that is equal to the resultant force. That means the resultant force also will generate the same kind of the effect. So in this case, the two forces are acting at the contact point, that is the normal reaction. Second one is the frictional force. That's I am going to be replacing with the R. So then in this case, the angle which this resultant component makes with the normal reaction is called the angle of the friction. So as we know, the normal reaction and the frictional force are in tangential to each other. It means that the both are perpendicular to each other. The normal reaction force is going to be passing between these 2 points, that is inclined to the frictional force as well as inclined to the normal reaction. So then in this case, the angle between the normal reactions and the resultant component is called the pi. So in this case, that I am going to be taking, when I am going to be construct the diagram, one is going to be horizontal force is going to be your frictional force, the vertical is going to be your vertical component is going to be the normal reaction, but the closing side is going to be called the diagonal of your resultant, and that's we are going to be taking. In this case, I am going to be taking the tan pi. The tan pi is equal to opposite side is going to be the frictional force, adjacent side is going to be your normal reaction. That's going to be F by N. So F we know that is equal to mu into N. When I am going to be substituting in this equation, then finally tan pi is equal to mu where I'm going to getting. Here the angle of the friction tan pi is equal to the coefficient of friction. So here I'm going to be representing in graphically. So one horizontal plane, at the same time one rectangle box I have taken, I place it on that surface, and it is going to be assumed that there is an interlocking is taking place in your horizontal plane as well as your rectangle box contact surface. So then what will happen? As you know that the self weight is going to be acting vertically downward direction. At the same time we are applying the force, try to make the body move towards the right side. So then what other forces are going to be developing? In this case, the first one is going to be the normal reaction force is going to be generating. At the same time, the frictional force is going to be trying to oppose the motion of the body. The normal reaction is trying to restrict the body move in the vertically downward direction. In frictional force, already we told, it is always acting tangentially to the contact surface and always opposing the motion of the body. That's why the body is trying to move towards the right side, but interlocking particles are going to be trying to opposing that motion, and that is going to be towards the left side. So then in this case what will happen? So there we need to find out, at the bottom surface contact we have two forces, normal reaction as well as the frictional force. I don't want to go with these two, then I'm going to show with the resultant component. It means that the particle not moving in the normal reaction direction or the frictional force, it is moving in the other direction, that is going to be the resultant component. So then the angle between these two we are going to be say, what is the angle? The vertical component of your normal reactions and the resultant component of the R, we have the pi. So this pi is going to be called your angle of the friction. So what is our outcome from this discussion? We do have discussed about what is the loss of dry friction. Here the loss of dry friction means one should have to feel, one should have to experience, then only this is going to be the law. The theorem has the proof, but loss one should have to experience, then only that will become the loss of the dry friction. Next one we have discussed about what is the angle of the friction. The pi we have calculated, that's going to be tan pi is equal to the coefficient of friction we have. And next one is the resultant reactions we have seen, and how we converted normal reaction and the frictional force into a single force. Next one, the practicing of the free body diagrams for the frictional surfaces. Thank you. We are doing a series of educational videos on engineering mechanics. For more updates, please follow my channel.